Bismillah ar-Rahman ar-Rahim. Welcome back to our course on deep learning for computer vision. Today we are going to continue our work on this course, and our lecture number is 13, and we'll see what it's concerned with. Actually, we are going to talk about the what we call it the activation functions. So let's jump to the course and see to the lecture and see what we're going to do with it. So as you see here, this lecture is numbered as 13, and its title is Activation Functions in DNNs and DNNs. In this lecture, we are going to talk and deal with the following issues. Why the activation function? What are the types of activation functions? We'll talk about linear activation function, sigmoid and softmax, ReLU, versions, etc. All these activation functions are going to be discussed, and we, by the end of the lecture, we will have some examples on numerical examples on these activation functions. Well, here, let's go back to a simple DNN. As you hear from this picture on this slide, if we recap what we have learned before, here we have the inputs for a specific DNN. In this case, these inputs will be multiplied by proper weights, W1 down to Wn, and a sort of summation will be applied to it, as you hear, and we add here a bias to the output. Then we send this to the what we call the activation function. This is the part where we are going to discuss today and deal with. After that, we'll get the output. We'll get the output as y dash or y hat. It's a result of applying function g to the output obtained from the network at this stage. So what is the activation function in this case? It's typically used to introduce nonlinearity. Usually, you know that the values after multiplying by the weights and adding the bias, when having a lot of nodes and a deep neural network, in this case, we may need to calibrate our outputs and take or get it into a specific range. And this will be done by using the activation function. This is not only the main task or the main objective of the activation function. In fact, we can see that it adds a sort of nonlinearity to the output of the what we call it the neuron or the perceptron, and after applying this activation function, we'll get the output in terms of the output of the activation function itself. So mainly, it is a nonlinear operation, nonlinear function that adds nonlinearity to the network, and this gives us an ability to extract and then learn more features or more complex patterns obtained by applying this activation function. As see here, we have the inputs from here. So we multiply it by the weights, then we sum, add the bias, and apply the activation function to get the output as a result of the this operation. So what are the main purposes of the activation functions? It's clear that step one, we may have here to add nonlinearity, as we have just mentioned before. So we can add nonlinearity. This linearity will help us to use different functions to modify and to calibrate our output into a specific range. This will cause the output to be a sort of nonlinear output of the applied input to it at this stage. Now, another very important feature is to allow back propagation. We'll talk about this in details in next lectures. Now, if you want to see or to track the improvement or the performance of your system, your ANN or DNN, you need sometimes to see what are the changes made on the weights and the biases. In this case, you need to measure the error or to find the modification or the rate of change in these values. In this situation, you need to have uh, a sort of feedback to the system in order to either to increase or decrease the values of the weights at a specific neuron or maybe at another one. And in this situation, you need to have, or you'll be able to see what's going on and improve the performance of the system, um, uh, uh, either ANN or DNN. And this allows you to find the rate of change, or what we call the differentiation, or by the help of applying this backpropagation action or operation. Another very important feature of using the activation function is the fitting of the output. So what we mean by that, as mentioned earlier, now if we want, usually we may, after multiplying, as you see here, we may here multiply the inputs by weights and add these inputs to sum it and then add a bias. So this will lead us to the output. At this stage, we may get some outputs that are very irrelevant or very high, so, or maybe very small, or maybe very highly negative. So in this case, we need to avoid having an output in the range of minus plus infinity, and this can be done by the help of using what we call the activation function. So we have here main three purposes: to add nonlinearity, which gives us an ability to learn more information or more about complex patterns in the inputs, and to allow for backpropagation and to control our let's say improvement or performance of the overall system, and to apply the fitting of the output to get the output being within a specific range, instead of having some values that are very strange or maybe very high, like minus, that may approach minus or plus infinity. Okay, so this is the main idea behind using the activation functions in general. What are the types of the activation functions? In general, we may have a long list of activation functions. I have combined them in one slide as here. We may have different types of activation functions like identity, ReLU, sigmoid, softmax, parametric ReLU. All these activation functions can be used, and it depends on where we can use it and for what purpose, what objective, what is the objective or network to in order to use a proper activation function. In general, we may categorize the activation functions into two main categories. The first one is, as you see here, it is the linear activation function and the nonlinear activation functions. Okay. More precisely, we may take the first type, which is very simple. We call it the identity activation function. The nonlinear, we have a long list of such functions like sigmoid or logistic, tan-h, ReLU, binary, soft plus, softmax, and other. The list is very long, and it can be updated every time by adding a new very interesting activation functions according to the application and the problem under consideration. Let's start with the simplest case. This is the activation function, which we call it the linear or the identity, as here from the equation. As you see here from the equation, let's see. Let's have a look on this equation here. Okay, we have y, the output y is equal to g of x, which is equal to x, which means that y is equal to x. So we did not modify anything at this stage. What for? Why we use it? Why we need it to just to have the output as the input? In fact, in this case, as I just mentioned, the output is the same as the input. Also, the output will not be confined between any range because we don't have any application or modification on the output applied, on the input applied to this activation function. Also, it looks helpless when we talk about or when we deal with very let's say classification tasks or let's say maybe regression function applications when we have a complex data and the features are not very well and very clear to be identified and classified. It seems obsolete. Why? Because there's no meaning for using a function that gives you the output as the input. So what for? Now in the regression task we may use this function because we don't want to have to confine the let's say the output within a specific range. Also, it's done for layers consistency. Sometimes you just need to transfer the input directly to the output without having any change. This will be very helpful in when we use the linear or the identity activation function. A very popular and used almost everywhere is the sigmoid activation function. The sigmoid or the logistic activation function. As here, we have the function applied to the variable z. In this case, z is the input to the current stage. It will be equal to 1 over 1 plus e to the power minus z. So this is the sigmoid function. And if you look at the shape of the function here, you can see that this function is mainly looks like an S shape, as an S shape. Okay. It's very simple mathematical description. It's very useful in many applications as will be seen. So it has an S-like shape. It exists as you see here from between 0 and 1. So whatever the value of z, the result will be always between 0 and 1. When you replace any value from minus to plus infinity, you'll get all values transferred or mapped to the range between 0 and 1. This is because of using this term here, as you see. Also, it's differentiable at any point. Why we need it to be differentiable? Because as I mentioned before, that when we want to check or to use the back propagation, it's a sort of feedback operation that is used to control our modification on the weights and let's say the biases. So when we modify W's and modify the V values, in this case, this modification could be can be done either randomly or on purpose. But sometimes you need to know to find the rate of change and what is the effect of this rate of change. If we want to find the rate of change, so you need to find the derivative, the first derivative, and this means that your function must be differentiable to be in the safe side. Okay. So where we can use the sigmoid or logistic activation function, it is very suitable for models that predict the output as a probability. So when we want to make our judgment or to decide what output to pick or to select or to classify, in this case, the inputs will be using this activation function will be mapped into different values of probabilities. And this will help us to pick the element or let's say the output that has the highest, for example, or maybe not only the highest of all, but the values having the highest values of the probabilities at the output. It can be also suitable for binary tasks. Of course, we have outputs. In this case, we have one or two outputs, either, for example, a dog or not a dog, maybe a dog or a cat. In this case, we may use the activation function, or the sigmoid, or the logistic activation function in order to get two values, for example, 0.9 and 0.1. This means that 0.9 is higher in probability, and this means that let's say the output having this probability is the most probably will be the output at this stage. So let's say for the dog we have 0.9 and 0.1 for the cat. This means that this output or what we apply to the input is classified as a dog, because we have a 0.9 probability, for example, and not for as a cat, that will be, for example, 0.1 of probability at the output. Sometimes the sigmoid is not enough. Why? We can use other activation functions. The logistic sigmoid can cause neural network to get stuck at the training time. What does that mean? Sometimes you may train and you you may get many iterations and a lot of epochs. We call it the epochs, and we'll talk about this later on. You'll get stuck in when you have what we call it local minima or local minimum. In this situation, you will get stuck with this point, and you will repeat your process many times and over, but without getting an improvement in the performance of your system. And this sometimes the sigmoid will not be helpful or not be quite enough for our to get the best performance from the system or from this neural network or from the deep neural network. To override this problem, we can use the softmax function or the softmax activation function. In fact, the softmax is a generalized version of the logistic activation function and can be used usually and very successfully with tasks that contain or that have a multi-class classification. What does that mean? Sometimes for many networks, you may want to classify the inputs, for example, in case of animals, into dogs, cats, camels, cows, maybe more classes. You may get up to maybe hundreds or maybe thousands of classes. In this case, you will be very satisfied with having softmax activation function instead of having only the logistic sigmoid, because the softmax is a generalized version of the logistic sigmoid or the logistic or the sigmoid activation function. Okay, a very important note here also that we can place our, let's say, the softmax at the final stages of the network in deep learning usually. While the sigmoid can be used in the intermediate stages, it would be very helpful. While when we have a lot of classes at the output and want to classify and to get good results, we need to place or to use the sigmoid, the softmax, and it will be placed maybe at the end or at the last layers of the deep learning network. Here, if you look at this simple example, here we have an input image. We're going to use a lot of layers here, as you see here. So this is our network, having maybe 1, 2, 3, up to maybe tens or maybe hundreds of neural networks with neurons and with biases, with weights, etc. So we get at the almost at the latest layers, what we call the logist L. So we have here, after mapping the result, we may obtain such values here before applying the softmax function. As you see, the softmax function here is it can be equal to e to the power z I for a specific feature value, and this will be divided by the overall for all the exponential values of all the inputs, in this case the logics, or maybe we can call it also the features or the samples or the outputs of the DNN layers. So as you see here that we at the output we have got output probabilities P. So for every input here at this stage, here for 3.2 we can get 0.775. For 1.3 we can get 1.116, etc. All these values give you the possibilities or the probabilities of what will be the output in this case. As here we have at the input we have a dog, and we have got for this class the highest value of the activation function, in this case the softmax. Okay, and this will help us to define and classify the inputs properly. So these values must sum also to 1 because the sum of all probabilities will be equal to 1, and this ensures that we are going to the right direction. So the softmax activation function, how it looks, it can be also modified as we have seen before. We have value here we added here a value of beta here in with the exponentials in this equation, and this beta is used as a hyperparameter that can be useful in improving our system or our neural network performance. Now this beta is sometimes called also the temperature. What is the effect of this beta? Usually when you pick high values for the temperature, this will give you an output with a more uniform output distribution, which means that you have higher entropy and more random outputs. While when you take lower temperature values, this will result in having a sharper output distribution and with one value dominating. So depends on your task, on your objective of your system or network. Usually, let's say we have a problem that where the outputs before the final stage, for the classification stage, you get probabilities that are very close to each other. For example, you have 4 classes, and these classes having the value of like 0.25, 0.24, 0.26, and 0.2, the sum of all these values. So when you pick one of the outputs, they are very close to each other, and your decision or the system decision on these values will be sometimes with errors. Why? Because the values of the let's say the probabilities are very close to each other. Now, what to do in this case? We can add this beta parameter, which is a hyperparameter again for the softmax activation function, and you can put it in your activation function in order to make these values a little bit be different from each other to give you better, let's say, thresholds for your decisions. How to select this value or to pick this value, you need to mainly for you as beginners, you can pick it randomly, then you will see a result, and you can correct the value and improve, increase or decrease according to what you get at the output. You can select a small input data set and see the result. However, you can find in the literature many techniques that or papers that deal with the value of beta and how to get this beta value within a specific range that is suitable for, let's say, your task. Okay. You can run this MATLAB code. Here we have the n value, which is a vector having or an output having 4 values, 0, 1, minus 0.5, and 0.5. When you apply the softmax for this n value, you will get modification in the values for these n inputs, and will give you distinguishable values for the output. You can run it and see it by yourself. This will be very helpful in understanding the reason for using this the activation function in this case. Another type of activation function is the tan-h activation function. The function itself is, as you see here, we have y equals f(x), where x is the input and y is the output at this stage. We have it as e to the power x minus e to the power minus x over e to the power minus x plus e to the power x. So this is called it's a tan-h function, and it's again very close in shape. It's see here in the red color we have the sigmoid, and here we have for the tan-h is the green one, and it's an S-like shape. The difference, as you see here from this curve, that this as you see that we have here values that extend between -1 and 1, and this gives you a wider range for the output to be making your judgment. So the tanh is also sigmoidal. It's a S-shaped function. It works better than the sigmoid when the range is the output will be between -1 and 1. In tanh function, the negative values or the negative inputs, let's say the inputs or the samples and the inputs will be mapped strongly negative for the negative values, and for the zero values, if you replace here x equals 0, you will get a value of which is near 0, and it will be almost 0. So it affects the values that going far away from the small values on the x direction, either in negative or in positive directions. So when you go further in x value, in a medium range of the value x, it will be more or less linear. For the 0, you'll get a 0 value. And when you go very highly in x, you get the S shape or the inclined line that going asymptotic line approaching 1 for positive x high values and for positive negative x high values. It's also differentiable, so again, it can be useful when you deal or when you have back propagation and to give you more control on your network. Now, as it's highlighted here in this box. In tanh, the negative inputs will be mapped strongly negative, and the zero inputs will be mapped near 0. So again, it depends on the output that you are aiming to have and to make your decision according to your performance of the system. Another type of activation functions is the rectified linear activation function, or we call it the ReLU, the rectified linear unit. And it's very simple, as here we have, if we have an input to the activation function is Z, let's take this function as R from the first letter in ReLU. Here we have the value will be, if Z is less than or equal to 0, will be 0, and otherwise it will remain as the input. So you see here our curve. So if you have values above 0, you will take linear operation. The output will be the same as the input, while when you take values with negative inputs Z or X, in this case we have Z, you keep these values or you set a value of 0 to all these negative values. So the RZ function is as a max function between 0 and Z according to the value of Z, whether it is positive or negative. So ReLU is actually in these days is very extensively used as an activation function because it's simple. It's almost linear for positive values, or maybe linear. You can say that it's linear, and it just maps the values for negative Z to 0. Most of the convolutional neural networks and deep neural networks in general use the ReLU in the mid-range of the mid layers, and it maps the values between 0 and infinity. ReLU also turns negative inputs to 0. It's also clear and cut here from this figure. Also, ReLU is differentiable everywhere unless for the value when we have the input as 0. And it's not a big matter when dealing with this. So usually you have to remember that the ReLU function usually is not usually used in case or at the output at the later stages of the neural network. It may be used in the mid values or the mid range of the network itself. Why ReLU is good and why it's used very commonly? Because of its simplicity and its computational cost is not very high. It's simple, sparse, and it has linear behavior. It may be a contradiction to have a linear behavior and you are looking for a non-linearity. In general, ReLU is non-linear, but its inside point of view, or inside view of the ReLU function, it looks like to be having a linear operation for the positive values of the input z or x in this case. What else? ReLU has a lot of versions. I call it here ReLU and its sisters. Here we have leaky ReLU. As here we have the ReLU function, it's very clear at the left-hand side. And here we have the leaky ReLU at the right-hand side. So the modification done here, as you see, that we have changed the behavior of the negative, the output of the negative inputs, where we have the function f of y equals a multiplied by y. So when we have the input with a negative value, we scale by a value of a. Now, what is this value? It's a constant value for this function. In general, when we have a value of a that is equal to 0.01, we have the function is called as leaky ReLU. However, if we can pick other values rather than 0.01. In this case, we can call it as a randomized ReLU. Now, what is the benefit of having this function over the ReLU function? As you see that it takes a portion or a scale or a part of the output for the negative values of the input. Instead of having it 0, it has been set to some scaled value ay. So this leak helps us to increase the range of ReLU to be having the range between minus infinity and plus infinity. However, the function is again linear, non-linear in general, but linear. It's a piecewise linear operation of function, and this helps sometimes to aid our objectives or our goals to have such outputs. However, this ReLU, which is called a leaky ReLU, is used usually in the intermediate stages of the layers in our network, whether it's deep neural network, CNN, or another kind of networks. Okay. Now it's confusing. We have many activation functions. What activation function to select in this case? Actually, we have some recommendations here. Very simple, but it's very effective and active. So they are, of course, the activation functions are very critical in deciding or to get or design a good neural network. Our previous knowledge of the network is needed here, and to make it easier to be implemented, we need to properly select the activation function. Here we have some key recommendations. The first one is, as here, that the default activation function for hidden layers is the ReLU function. We can use leaky ReLU. Actually, I used to have ReLU and leaky ReLU, and the performance was not very strongly changed. The improvement sometimes is not very high, and this will be at the expense of having some additional computation cost when we use leaky ReLU over ReLU. If we are talking about regression problem or issue or task, we need to have to select or to pick the linear or the identity activation function, because there we don't have a limitation on the output because we don't have a decision to make on this output for classification tasks or for sure. Now, when we talk about classification tasks, it would be better to use the softmax at the output stages, while we can use we can use the logistic or the sigmoid at the intermediate stages or layers of this network. And again, it's an art actually. Deep learning is not, of course, it's science, but it's an art, because sometimes not everything is explained here, because when you deal with random inputs and random variations of the inputs. This will, let's say, affect the system. And when you change this piece or that piece by replacing the activation function, you may get some improvement due to the usage of or utilization of specific or let's say some activation functions that cannot be explained always. You may just give generalizations. So these are just recommendations, general recommendations, not very specific, but it can be used and they are working very well in neural networks in general. Let's recap this topic. So the problem type defines the usually used, what we usually use as an activation function. If you have an classification problem, you can, for the classification, we may find different types of classification. You may have just binary classification. So in case of binary classification, you have only two classes at the output, either 0 or 1, or maybe dog or a cat, a camel or a cow, faulty or operative piece of technology. In this case, you have it's recommended to work with or to use the sigmoid activation function. If you have a multitask classification problem, so at the output you may get a lot of classes, maybe maybe 3, 4, 5, up to maybe hundreds. In this case, you the latest layers, you can pick the softmax activation function, which is working very well and very nicely. Now, if you have a multi-classification, multi-label classification, what does this mean? You may have one, let's say, one input image or one input sample, and you want to give not only one label, so you can say that this part is working and this part of this image is not working, and we have a problem at this corner or that corner. In this case, you have in the same image or in the same input, you may you may get a lot of labels, maybe 3, 5 labels within the same class. In this case, you can use again the sigmoid activation function to apply the nonlinearity at this stage. If you are talking about regression issue or problem, it was discussed in the last lecture, in lecture 12, maybe part 2. It would be better to have a linear activation function, which is the identity activation function. Of course, this is not always the case, but in most of the cases, you can follow these instructions and take use of these recommendations. Here we have, let's say, cheat sheets. So you can see that a lot of activation functions on one paper, one page, and you can here see the positives or negatives of the pros and cons, we call it, for every activation function. And we have, for example, here we have the sigmoid function, its derivative. We can use it logistic, binary, in regression and in binary classification. Here we have the tanh or tanh. It was used in the late 1990s. Here, this is the function. Here we have the derivative, where we can use it here. It's clear, and so forth. You can have a look on all these functions. Not only these, you can have also other activation functions, as you will be see on the next slide. Here we have also Likirilu. We have its derivatives. Here we have the exponential linear unit, ELU, etc. You can have a look on all these activation functions and search the net for specific details about every single component of these activation functions. And the list will be always updated. It will not stop at this point, for sure. Taken from the net, from this, the page of this Adriaman, I think Kenthi. Okay. So let's have an example here. Given this simple linear network, we have this input. These are the weights and the values for the input. Here the weighted. Here we have the neuron having the activation function. and the weighted sum with bias of 2. What we are asked to do is to find the value of the weighted sum value z, this value z. See here. So this is what we want to find, z, here. If the classification is binary, suggest a strong activation function. So here the output, we want to have a binary classification, binary, for 2. For 3, assuming that we have a binary classification function, find what will be the output of this case, then comment your results and explain what you have done in these stages. Let's go to the solution. Now we want to find the value of the weighted sum value z. Here it's minimized here, if you have a look at this corner. So as see, we have z is equal to w1 multiplied by the input x1 or a, and w2 multiplied by the input x2 or b. Then we add the bias, which is equal to 2. So this is our output. It's clear from here. So we have 0.5 by 2 plus 0.3 by 3 plus 2, which is the bias. We get a value of 3.9. The second question was, if the used classification is binary, suggest a strong activation function. What do you think? In case of binary activation function, binary classification, it is recommended to use the sigmoid activation function. Let's see if it's true or not. Sigmoid is suitable for this function, okay? Assuming that we have a sigmoid activation function and we have a binary a classification task, let's find now what will be the output y in this case. The output will be f of z, which is 1 over 1 plus e to the power minus z. Z in this case will be the result of part 1, which is 3.9. So we replace z by 3.9 and get a value of 0.98. So what do you think? What is this mean? What does this mean? 0.98. It's a high value for the output. So what we can comment on this? So the value of 0.98 can be interpreted as the strong probability for sure. 0.98 is almost 1, so you are very close to 1, which means that the probability of the neuron is belonging to this class. Okay, it is very important when we have such a situation. Of course, this is not the case every time, because when we want to, not always we can get such high values for the probabilities. However, if we get values like 0.9, 0.8, 0.75, or more or less, we can judge that this is good for this case. Another example. So here we have, this is the input tensor, and we want to find out the output of the activation function, assuming that this is the input coming from the previous stage. So this is our input coming from the previous stage. We call it tensor. Tensor is used by Google, and we have some information about the tensor itself. It's a sort of a generic structure that can be used for storing, representing, and changing data. Tensors are usually used by machine learning and by the deep neural networks. This term, TensorFlow, was taken from the Google's TensorFlow because tensors are essential to this discipline. Of course, for me and for you to understand easily, at this stage, before applying the activation function, if you have a network or a system, or let's say having some outputs, you need to map these outputs into a vector, and this vector is simply the tensor. Now we are asked to find the output. Suppose that we have this input tensor to our activation function at the latest stages or layers of the network. We want to find out what will happen if we'll use the first time ReLU, then leaky ReLU, sigmoid, softmax, tangent, etc. All these activation functions can be used here, and we can see the effect of getting or having these different activation functions to this input tensor. In case of having ReLU, this is the input tensor having all these values. We have 1, 2, 3, 4, 5, 6, 7, 8 inputs. We apply it to ReLU, and we'll get the output these values. As see here, we have just modified the values with negative inputs. Okay, this is for the first case when we have a ReLU case, and also for the last one. This is for ReLU. Now, if we have leaky ReLU case, now what will happen? We again we are not going to modify these values for this one, this one, this one also, this one, and this one. So what will happen to the negative values? They will be multiplied by a scale. So if we have value at the input minus 0.24688, it's around minus 0.25. We just multiplied by the scale A, which is equal to 0.01 for the ReLU, and this will give us a small negative value. Again, for this one, we have a small value. Again, here we have also another small value. Actually, the leaky ReLU could help us in avoiding what we're calling the dying ReLU case. And I encourage you to read some references maybe on the net, on the www. They say Geeks for Geeks, and this will be very helpful in finding or understanding what is the purpose of using leaky ReLU in order to keep some small part of the let's say negative inputs or in the tensor input tensor to be mapped to the output without getting it set to 0. In case of the sigmoid, this is the output. Wow! So we are going to combine all the inputs in our apply the sigmoid function and get an output. So in this case, we have a value of 3.946. Of course, it's not let's say the combination is very small here because the values are very small also. So you can see that the values are not very high. So the output will be also just one value. So one output for the sigmoid in case of using the sigmoid. Let's go further. What will happen in case of the softmax? So you can see that the inputs tensor having these values, they are mapped to the output values like this one, etc. Now you can see that the highest value for all these is this one. Okay, this gives you an indication of, okay, maybe no, not this one. Okay, I'm sorry. It's very close. Again, this is a problem. This is a good question because you see, if you look at this one output, these are two outputs, you can see that we can pick this one as a decision for our, if it is the last stage in your network. But we have here a value. This one is very close to this one. So we may go now to pick the beta value in order to make it distinguishable and make our decision more proper, because you may decide that this is the output which has a probability of 0.2829, and it's very close to this one, which is 0.28, the first one, which is 0.2815, and this may lead you to give an error classification. So when you add the beta parameter, this will make these values be changed according to your selected value of beta. Then you'll check, my decision is okay, so I keep this beta. My decision is not okay, I can modify until I reach the best case. Of course, you can find in literature what is the commonly used value for, empirically used value for the beta hyperparameter. So you can see all these links and have fun in reading and listening to these some of these videos and some these pages. You can have some questions and examples on that. Hope that it will be interesting for you, and hope that you are now very familiar, or you can have a good basic idea about the activation functions in general. And that's all talk for this lecture. See you soon.